In the previous video, we wrote all formulas that we need, and now let's apply them. So the first problem that we will solve will be, let's prove that force of gravity and force of spring are conservative forces, which means that we need to find the potential energy function, U, for force of gravity and for force exerted by ideal spring. Now, let's write again the definition of conservative force. The force is conservative if work done by this conservative force does not depend on path. So if I move my object from point x1, y1 to point x2, y2, then I can go this way or this way or this way. It doesn't matter. Work does not depend on dr along which I will be moving. Work done by conservative force is integral from r1 to r2, from r1 to r2, f dot dr, and it is equal to minus some function that we call potential energy function at the final point, minus u at the initial point. From this equation, it follows that x component of force is partial derivative minus du dx, and y component of force, Fy, is minus du dy. Now let's think for a minute how powerful this statement is. So if you have a scalar potential energy function that exists at each point of space, you just put numbers at each point of space, you can retrieve the vector. You can retrieve both components of force, which is a vector. So we need to learn how to solve two types of problems. Type number one. We are given a force, and we need to prove that force is conservative. So we need to prove that potential energy function exists for this particular force. And another type of problems that we have to be able to solve is when U is given, we have to be able to take partial derivatives with respect to x and y and find both components of force. So far, we will be solving first type of problems when force is given. For example, it is force of gravity. So here is the point, and there is force of gravity acting on this object that is at this point. Force of gravity, mg, it is down. Force of gravity as a vector in my coordinate system with y up is minus mg, j. Or in terms of components, f sub x is 0 and f sub y is minus mg. What I want to do, I want to find the potential energy function for force of gravity. Or in other words, I want to prove that this force is a conservative force. How to do that? I will use the definition of conservative force. So I will write work done by force of gravity. When I move the object from arbitrary point, this is important. I move object from arbitrary point x1, y1 to arbitrary point x2, y2. So here will be my force of gravity dot dr. And this has to be equal to change in potential energy function, U, at the top point minus u at the initial point. I'm sorry, let me take the eraser, and just to save the space, I will write u1. So this is u, no, I changed my mind. We will not be saving the space. I will rewrite it one more time. So force gravity dot dr, and this is equal to minus u at x2, y2 minus u at x1, y1. Okay, so what is this integral? We know that this integral is integral from x1, y1. This was the previous unit. x2, y2. We calculated work many times. fx dx I'm writing this dot product f sub x dx plus integral x1 y1 to x2 y2 fy dy. F sub x is 0. F sub y is integral of minus mg dy. And this integral is from y1 to y2. Nothing depends on x. And this is equal to, I take this integral, it is minus mg y2 minus y1 minus mgy, I plug in the limits. And this has to be equal to minus, by definition, u at, I skip x2 because nothing depends on x, u at y2 minus u at y1. Now I compare the left and right hand sides of these equations, and I combine guys with 2 and with 1, and I immediately see that u at y2 is equal to minus minus plus mg y2. U at y1 is equal to mg, here plus, here minus minus plus, mg y1. And since y1 and y2 are arbitrary points, this is important, arbitrary points, this works for any y. So u as a function of y for force of gravity is mgy. And I will add constant. Why? Why would I add arbitrary constant? Because potential energy function is defined with respect to constant. And now what I will do, I will differentiate u back to make sure that we get all information about our force of gravity. Where will I write it? I don't have space. I will use red, and we will do it right here. So, and you know what? We don't need this graph anymore. So that's where we will save space. Let me erase this graph real quick. Again, what will we do? We will differentiate potential energy function back, making sure that we retrieve all knowledge about our force. So what is F sub x for gravity? It is minus du dx. I differentiate this and I get 0, of course. Nothing depends on x, and x component of gravity is 0. We are happy. Now what is Fy for gravity? It is minus du dy. I differentiate my u with respect to y. We don't forget about this minus. So my result is minus mg, and derivative of constant is 0. So I retrieve both components of gravity. We have our force of gravity. Back as minus mgj. Wonderful. This will not be the same for non-conservative force of friction. But force of gravity is conservative force. We proved it by finding the potential energy function for force of gravity. Now, is there another way to do that? Yes, and the second way is much shorter. That's why I will show you the second way. But before I show you second, let me repeat the steps for the first way we did it. We wrote the definition. So this is the definition of conservative force. Work done by conservative force is minus change in potential energy function. After that, we calculated work done by gravity when we moved object from one arbitrary point to another arbitrary point. This is arbitrary. This is important. So we compared left-hand side, right-hand side, and we figure out that u at any point y, u as a function of y, is mgy, and we added constant, because we understand when we differentiate back to make sure that we retrieve all information about force of gravity from our potential energy function, derivative of constant will be 0. So we differentiate back, and yes, it works. We proved that force of gravity is conservative force because the potential energy function exists, and we know it. Now, second way of doing that. Second way works for one-dimensional problems only. One-dimensional only. It will not work for two-dimensional problems. Is this a one-dimensional situation? Yes. Force of gravity has just y component, no x component. Then my first line will be the following. Let me erase this real quick. Since force of gravity has just one component, so we can think about this as one-dimensional problem. Force of gravity is minus mg, it has just y component. My first line will be Fy equal to minus du dy. Now, if I integrate both sides of these equations with respect to dy, I will have Fy dy, and this is indefinite integral, is equal to, I didn't erase this well, is equal to minus integral du dy. Now, what is the right-hand side? This is antiderivative, so this is equal to minus u as a function of y. So u as a function of y is equal, I bring minus to another side of equation, minus Fy dy. Okay, great. So it is minus from the definition. And then it's integral Fy is minus mg dy. We keep going. Please remember, those are indefinite integrals, minus, plus. Guess what? It is mgy and plus constant, it's indefinite integral. We know that we need to add constant. So it is the same expression. It was just twice shorter. And when you deal with one-dimensional problem, I would recommend you to start with this. Then you integrate both sides. You understand that u is minus integral Fy dy. You integrate Fy, and you get the potential energy function. Then you can differentiate back, follow the same procedure, and yes, you get your force back. So one way or another way with definite integrals and arbitrary limits from definition, or indefinite integral, but don't mix these two. So if you put here delta v, that would be a mistake. It is delta u. It is just u as a function of y. It's not definite integral. It's not u at upper limit or lower limit. This way it is shorter. That's why I thought that I will bring it here.